Section: Introduction. In this section, we discuss the growing use of proprietary large language models, LLMs, and the privacy issues they raise regarding users' sensitive information. We introduce private inference, PI, as a potential solution that allows computations on encrypted data without revealing its contents. However, we face challenges in implementing PI systems due to high latency and communication costs, especially with transformer-based LLMs. For example, generating a single output token with a GPT-2 model takes over 8 minutes and requires significant data transfer, which increases with larger context sizes. These inefficiencies stem from the complex nonlinear operations necessary for model performance. In privacy-preserving contexts, these operations rely on secure multi-party computation, MPC, protocols and cryptographic techniques, which involve multiple rounds of communication, further increasing costs. We note that nonlinear operations, particularly JLU and layer norm, are major bottlenecks, contributing significantly to latency and communication expenses. To improve efficiency, we explore designing LLMs with fewer nonlinearities. However, the essential role of these nonlinearities in maintaining model effectiveness and information flow is not well understood. Previous studies have looked at specific aspects of nonlinearities but have not fully addressed their impact on model stability and attention diversity in multi-layer LLMs. To fill this gap, we propose an information theoretic framework to analyze nonlinearities in transformer models. By applying Shannon's entropy, we reveal that nonlinearities play two key roles. They help maintain training stability and support the diversity of attention mechanisms. Our contributions include 1. PI-friendly layer normalization alternatives. We investigate static normalization methods, like weight and spectral normalization, to reduce training instability without relying on layer norm. 2. Entropy regularization techniques. We introduce an entropy-guided attention mechanism and a new regularization technique to manage entropic overload in LLMs with fewer nonlinearities. This includes adjustable thresholds for each attention head and tolerance margins to maintain diversity. 3. Practical design for PI. We implement our entropy-guided framework and test its effectiveness across various context sizes and model depths using diverse training datasets. Our analysis of entropy dynamics helps us understand how simplifying architectures affects training stability and attention diversity. In summary, we establish entropy dynamics as a foundational approach for optimizing privacy-preserving LLM architectures. Section Summary. In this section, we discuss the privacy concerns associated with proprietary large language models and introduce private inference, PI, as a solution that allows computations on encrypted data. We highlight the significant challenges in deploying PI due to high latency and communication costs, particularly from nonlinear operations, and propose an information theoretic framework to analyze the role of nonlinearities in transformer models, aiming to optimize architectures for efficient privacy-preserving applications. Section: Information theoretic analysis of nonlinearity in LLMs. In this section, we systematically separate nonlinearities from transformer-based decoder-only large language models, LLMs, to explore their effects on training dynamics and the expressiveness of the attention mechanism, using Shannon's entropy as our framework. Shannon's entropy helps us measure the uncertainty in a probability distribution, indicating how much information is needed to describe a random system. For a given probability distribution, we define entropy as the negative sum of the probabilities multiplied by the logarithm of those probabilities. In a softmax-based attention mechanism, each softmax operation gives us an entropy value that reflects how spread out the attention scores are for each query position. A higher entropy means the scores are more evenly distributed, while a lower entropy indicates a focus on specific features. We denote the attention matrix for the HTH head in the LTH layer as a square matrix, where each element represents the attention weights for a specific query and key. This matrix is created by applying the softmax operation across the key length for each query. We then calculate the average entropy across all query positions to get a single entropy value for each head. The entropy for the HTH head in the LTH layer is computed with a small constant added for numerical stability. We start by examining the headwise entropy distribution of our baseline architecture using JLU and ReLU in their feed-forward networks, FFN. We find that about 90% of the heads have entropy values between 1/4 and 3/4 of the maximum observed entropy, indicating a well-behaved distribution that serves as a benchmark for understanding the effects of nonlinearities on model behavior. However, we notice that in some configurations with reduced nonlinearity, many attention heads show higher entropy values, which we call entropic overload. We believe this shift from a well-behaved distribution leads to underutilization of the network's capacity, as too many heads are exploring rather than effectively using the diversity of attention heads. Our visualizations reveal significant entropic overload in the early layers of specific architectures, particularly in the layer norm-free model with JLU and the softmax-only model without layer norm and FFN activations. In the layer norm-free JLU model, 58% of heads have high entropy values, compared to only 23% in the layer norm-free ReLU model. Additionally, fewer heads in the ReLU model reach maximum entropy, leading to an improvement in perplexity. In the softmax-only model, 45% of heads also show high entropy values, with many nearing the maximum. We observe that the lack of layer norm and FFN nonlinearity in the softmax-only model results in entropy collapse in deeper layers, characterized by near-zero entropy values, which indicates training instability. About 33% of attention heads show entropy values close to zero, contributing to this instability and highlighting the importance of nonlinear components for stable training. To address these issues, we explore techniques to prevent entropy collapse without layer norm and FFN activations. We introduce an entropy-guided attention mechanism along with an entropy regularization technique to manage entropic overload in models with reduced nonlinearity. Instead of relying on layer norm, which is computationally expensive during inference, we focus on weight normalization techniques that do not involve nonlinear computations. We find that weight normalization and spectral normalization can effectively prevent entropy collapse in deeper layers when applied correctly. We also simplify the LLM architecture by creating a softmax-only model that merges two linear layers in the FFN into one. However, this simplification leads to challenges, particularly entropy collapse in deeper layers. To counter this, we implement a scaling method in the FFN that uses learnable factors to stabilize training more effectively than weight or spectral normalization. To maintain diversity among attention heads, we develop an entropy-guided attention mechanism that allows the model to adjust entropy patterns during training by modifying the temperature of the softmax operation. Higher temperatures increase entropy, while lower temperatures decrease it. For our entropy regularization scheme, we aim to manage higher entropy values, which involves adjusting the regularization strength for each attention head individually. We set dynamic thresholds based on the characteristics of each head and allow for small deviations to prevent over-regularization. We also establish a maximum entropy reference to ensure consistency across different layers and heads. In summary, we present a comprehensive approach to understanding and managing the nonlinearities in LLMs, focusing on entropy as a key factor in training dynamics and model performance. Section Summary. In this section, we analyze the role of nonlinearities in transformer-based LLMs by examining the entropy of attention score distributions, revealing that well-behaved entropy distributions are crucial for effective model training. We identify issues like entropic overload and entropy collapse in models with reduced nonlinearity, and propose an entropy-guided attention mechanism and regularization techniques to enhance training stability and maintain attention diversity. Section: Experimental Results. In this section, we present our experimental results. We set up our experiments using a secret flow configuration, simulating the client and server on two separate machines, each with an AMD EPYC 7502 server featuring a 2.5 GHz processor, 32 cores, and 256 GB of RAM. We measured the total latency for processing, including input and output layers, in a wide area network setting with a bandwidth of 100 megabits per second and a latency of 80 milliseconds, using Linux traffic control commands. We utilized 32 threads for our operations and trained all models on a single RTX 3090 GPU. For our models and datasets, we trained GPT-2 models with 12 and 18 layers on the CodeParrot and Languini book datasets, which are recognized benchmarks for large language models. The CodeParrot dataset consists of 20 million Python files from GitHub, totaling 8 gigabytes and containing 16.7 million examples, each with 128 tokens, amounting to 2.1 billion training tokens. We used a tokenizer with a vocabulary of 50,000 and trained with context lengths of 128 and 256. The Languini dataset includes 84.5 gigabytes of text from 158,577 books, totaling 23.9 billion tokens, with a vocabulary of 16,384 and a context length of 512. Each book averages about 559 kilobytes of text, or around 150,000 tokens. Regarding our training hyperparameters, we followed established settings for both the CodeParrot and Languini datasets to ensure consistency across different model architectures. For the CodeParrot dataset, we initialized the learnable temperature for entropy regularization at 0.01 and set the lambda parameter to 0.00001. For the Languini dataset, the temperature was set to 0.1, with lambda at 0.00005. We found that entropy regularization helps prevent extreme entropy values during training, leading to a more balanced distribution and improved performance, as indicated by lower perplexity. We also observed significant variability in the learnable threshold parameters used in our entropy regularization scheme, which allows the model to adjust the regularization strength based on the specific roles of different attention heads. This adaptability is crucial for optimizing the regularization process for each head's unique requirements. To avoid over-regularization, we adjusted the threshold margin using a hyperparameter called gamma. This adjustment ensures that a sufficient number of attention heads maintain higher entropy values. As we increased gamma, we noticed a rise in the proportion of heads in the higher entropy range, with gamma set at 0.2 yielding the best performance in terms of lower perplexity. We also analyzed the dynamics of entropy during training, finding that as gamma increased, the mean entropy of the early layers rose, which is essential for maintaining the diversity of attention heads and preventing over-regularization. Our results for the GPT-2 small models showed a significant reduction in communication overhead and an improvement in end-to-end latency due to architectural simplifications. Additionally, entropy regularization improved the perplexity of our models, confirming the effectiveness of our approach. Finally, we demonstrated the scalability of our methods across different model depths, context lengths, and training data sizes. Our experiments showed consistent benefits in nonlinearity reduction and the effectiveness of entropy regularization, regardless of the training scale.